to the Uncommon Living podcast, where we host dialogues in human resilience. I'm Thomas Seager. I'm a professor in the School of Sustainable Engineering at Arizona State University and the CEO of the Morozko-Forge Ice Bath Company. My guest today is Professor Denis Blondin, who is the world's foremost expert on cold activated brown fat. In today's episode, he takes us through a tutorial on the metabolic mechanisms by which brown fat can improve health and well-being in the body. And he corrects many of the misconceptions that medical doctors and other scientists still harbor about the formation and action of brown fat inside adult human beings. Denis Blondin, thank you for joining me on the Uncommon Living podcast.
Thanks for having me. It's great to be here.
Your name comes up more than any other scientist when I go through the library trying to learn about cold thermogenesis, trying to learn about brown fat. I see paper after paper with you as a co-author. And I thought I should probably learn how to pronounce your name because I know you're in the French-speaking part of Canada. My French is terrible, and I'm probably Americanizing your last name in a terrible, mispronunciation. Will you tell our audience how I should say it, even if I can't get it right?
Sure. Yes. So I'm Denis Blondin from the University of Sherbrooke, and as you mentioned, we're just outside of Montreal, about an hour and a half, about an hour 45 outside of Montreal. So a nice quaint place here in Sherbrooke. Lots of mountains, nice and cold in the winter. So we love it here.
I don't know how you got interested in brown fat, but you've written a little bit about the interesting history of brown fat because it's not even been 20 years since medical doctors have acknowledged that brown fat exists inside adult human beings. Will you tell us a little bit about this revelation that has changed so many minds?
Sure. Yeah. I mean, we came into it kind of by chance in the sense that we had already been sort of working on the effects of cold exposure in humans, but in a slightly different context. At the time, we were interested in trying to understand how people can improve their survival and performance in a cold environment, whether they were as an athlete, so their performance as an athlete, or their performance as for military operations. And so we were trying to understand, what kind of foods should you eat in the cold, and for us to try to understand those sort of things, we also need to understand what organs are responsible for generating heat. So if we can understand what organs are responsible for generating heat, it might help us understand what kind of fuels we need to fuel it. And so we'd always been focused, especially on shivering, our shivering skeletal muscles. And then at the same time, there were these initial papers that had come out. The first one sort of in 2007 that kind of talked about the presence of brown fat in humans. In our papers at the time, we kind of talked about it we talked around it. We talked a lot about, we don't think the field doesn't believe that it's really present. The field doesn't really suggest that it has much of an impact. So we kind of talked around it. But then in around 2010 or so, we were approached by a researcher at the University of Laval called Denis Richard, and who approached myself and my supervisor at the time, François Hamann, and another researcher at the University of Sherbrooke named André Carpentier, whose expertise was in PET imaging. So we kind of brought the three groups together. Denis Richard was an expert in brown fat. We were the human experts on cold exposure. André Carpentier was the expert on PET imaging. And we kind of just came together.
PET is an acronym. Pardon me the interruption, but for
yes.
Our audience, PET is PET, positron emission tomography. It's not like you're going to take an image of your dog or something.
That's
like
right.
that.
Yes. Right.
This is
So
state of the art in detecting brown fat, but it was primarily for cancer imaging, and it's been adapted.
That's right. Yeah. So it was originally used for identifying tumors, for cancer diagnosis, and for treatment in some cases. But it was also the tool that allowed people to identify that there was this tissue that kept lighting up for a lot of sort of PET technologists and radiologists. They were sort of looking at this, and they knew it was around because they kept seeing, well, it keeps popping up on our images, and it's giving us these false positives. We know that these aren't tumors. because in part they're very symmetrical, so they come up in certain spots but very symmetrically, and they present very differently than a tumor would. So they would always pop up in these PET and these positron emission tomography images, often with using a glucose a tracer, a radioactive tracer. And so we combine these sort of three sort of skills and expertise, and that's sort of how we launched our research into brown fat. We were always still interested in trying to understand what role shivering is playing, but this was our opportunity to really start characterizing, the presence of brown fat in humans, how active it is, how much it can change, how it responds to different stimuli. So that's really what we've been doing since basically our first paper was published in 2012, and we've been working on it since then on trying to understand different facets about how this tissue functions in humans. And so part of the reason we've been able to kind of continue working in this area and building upon it is because of the infrastructure we have here at the University of Sherbrooke. We have a dedicated PET scanner. We have a radiochemistry lab where we can produce our own radioisotopes. So we can modify radioisotopes and use different types so we can get better information about what the tissue does itself. But yeah, that's kind of what launched us into this area. But like I said, originally there wasn't really any interest, and we'd really been talking around it. So we're kind of happy now that we know a lot more about it. And I think we've made a number of really interesting discoveries since then. And I think part of it was based, we made a number of discoveries that were kind of debunking a lot of things that were kind of common in the literature at the time. There was a lot of dogma in the field, which was largely based on animal research. And we realized that there was a lot of things that maybe don't translate as well. But yeah.
So you started working in military applications. Some of the best work in cold exposure and human performance has been funded by the armies of the cold weather countries. But I've never been satisfied with it because there's always been an enormous gap. They will, for example, model wind, clothing to try and get a sense of heat extraction. And they will model exercise to try and get a sense of heat generation. But these heat balance models have never really worked out in a reliable way. And now you're suggesting that what they've been missing is the non-shivering thermogenesis that can happen in a human body that is acclimated on a regular basis to cold. Is that about where you were in 2012?
Well, yeah. So ultimately, I think we were trying to understand, the biggest challenge with exposing someone to the cold, where a lot of the discomfort comes from, the part that becomes a challenge in terms of performance ultimately comes down to shivering. So shivering is the problem, right? Shivering is the problem because it impairs your ability to make decisions. It impairs your ability to focus. It is very costly. It impairs your ability to make certain movements, particularly fine motor movement. And so ultimately shivering is the problem. So our ultimate question was, well, how do we reduce shivering? Well, we reduce shivering, theoretically you reduce shivering by increasing mechanisms that will produce heat without shivering, which we call non-shivering thermogenesis. But that can come from a number of places. The idea was that, well, maybe brown fat is maybe the primary source of this non-shivering because it is in rodents. In rodents, it's very, very impressive. Rodents can go, once they're well acclimated to the cold, they go in the cold and they don't really shiver much. They rely a lot on their brown fat to generate heat. And so it was logical for us to think, well, maybe in humans it's the same thing. Maybe we can make this tissue grow. Maybe we can increase its activity. Maybe it's very adaptable. But at the time, we didn't really know. There are other sources of non-shivering as well in skeletal muscle. So we were also interested in those sources of non-shivering thermogenesis in skeletal muscle. But at the time, we thought, well, let's probe a bit further about what's going on in brown fat specifically, because this looks like it's an interesting target, one that seems to have a lot of potential because we see it changes a lot in response to changes in temperature. We know it's very important in rodents. Surely there's a way we can adapt it in humans.
There's never been much controversy about human infants or young children because tragic autopsies have revealed that they have plenty of brown fat. But the common wisdom, so to speak, or misconception among medicine was that we gradually lose this brown fat as we become adults. I'm skeptical. You live right outside Montreal. I've been to Montreal. I spent years of my life in northern New York at Clarkson University in grad school. I've been outside when it's negative 40. And it doesn't matter if you're talking Fahrenheit or Celsius, because that's where the two, temperature scales cross.
Yeah.
I've felt the cold. But when people come down to Phoenix and they spend a couple of years here after they move, they wind up putting on hats and big winter parkas. And, it might be 50 degrees Fahrenheit or even a little warmer. We call them now Phoenix wimps. And it takes a couple or 3 years for this adjustment to get made. I've wondered whether they've lost their brown fat after being in the heat of the desert for a couple or 3 years. Now that we know human beings have it, it's a big question. How did we ever lose it? Why do we lose it? And how long does it take?
Yeah, I mean, that's a good question. I mean, I think the challenge we have too is, again, this comes down to some of the dogma. I think the part of the reason that there was this sort of misconception that adult humans lost this brown fat is in part we were looking in the wrong spots. So infants, for example, when we talk about infants and babies have brown fat, they do have a lot of brown fat, but it's in a depot that's that's just on their back, between their scapula. And so it's a sort of big triangle depot, which is called an interscapular brown fat depot. And that depot disappears with time. It's the same depot that rodents have. And so that's why we thought, well, this is the target. This is what we're really interested in. But ultimately, that's the depot that disappears. But the other depots that are still found in other areas, so there's another depot that's just behind your collarbone, and it extends sometimes under your armpit. There's sometimes some individuals might have it around their kidneys or along their spinal cord. And so those depots were always there, but we weren't looking necessarily into those areas. We knew from older studies, again, autopsy studies that were done in the 80s, we knew that they were present there. So, for example, there was a study that was done in Finland where they performed autopsies on outdoor workers. So they were lumberjacks and construction workers, and they compared them to autopsies that were done in office workers. And you can see there were different depots of brown fat that were present in those outdoor workers. The interscapular depot wasn't really that present, but there were all sorts of other depots that were present. And again, we weren't looking there. And like I mentioned, with the advent of PET imaging, technologists were noticing it and were recognizing it, and they were saying, well, these are the spots we tend to see it a lot. But again, it didn't fit with the narrative of, well, that's not where brown fat is. Until, again, some work had been done and someone had taken biopsies and recognized, actually, this is actually bona fide brown fat. And so if it is brown fat, we got to find a way to tap it down a bit so it's not giving us these false positives. But it also meant that it launched this whole area of research. And now we know that it's very responsive to repeated cold. So we've done a number of cold acclimation studies where you expose people to cold every day for 4 weeks, and you see this significant increase in the amount of brown fat that's available. You also see that per gram of tissue, the tissue is much more metabolically active. What's interesting, though, is that regardless of how you do your cold acclimation or for how long, whether it's 10 days or 4 weeks, the volume of the tissue increases about the same. So there's that part we don't really understand, but it seems to, nonetheless, regardless of how you do your cooling, you're going to see some increases in brown fat, at least size. In terms of the activity per gram, again, the data is pretty limited, but we assume that if the size increases, then the activity per gram also increases. But so you see it's very responsive.
How does the body do this? How does the body restore brown fat or recruit new brown fat cells when they were absent, and then you start doing cold, and you do this for a couple of weeks or a month, and the next thing you know, brown fat is showing up in your body? What happened?
Yeah, I mean, that's another excellent question. One of the things that comes across a lot in the literature is trying to understand, are these new cells? Are these cells that have changed their composition or changed their structure and function? That part is still relatively unclear. I think there's still a lot of debate as to that. But ultimately, what we know is that you can have a depot that is an adipose tissue depot without going into the specifics. Is it white adipose tissue? Is it brown adipose tissue? Is it a mixture of both? what we think is there's probably a mixture of these adipocytes, these small adipose tissue cells within these depots, and they have the ability of fluctuating, but depending on the stress. So if you're constantly under a strong sympathetic stress, whether it's cold exposure or potentially even prolonged fasting or something like that, where you have this strong stress, or we see it in burn patients as well, then you have this ability to change the composition of those depots. The depots become much more brown. There's a higher presence of brown adipose tissue, and a lot less of this white adipose tissue. You see that sort of tends to, like I said, it's usually the supraclavicular depot that tends to shift a lot, but then it might migrate into sort of under the armpits. Again, for some people, that might also migrate down the spinal cord, where you have these little sort of lobules of adipocytes along the spinal cord. Not everyone has that. Only certain individuals do. But we see is that when you expose people to the cold, you get people who shift really, where they respond very strongly. They get all these sort of depots everywhere. And on the flip side, when you go take them out of the cold, so you have people who move to the south, for example, whether it's Arizona or Texas or Florida, it'll shift. It seems to shift back towards a whiter adipose tissue. And again, in part, it just probably has to do with the relationship with it's, how much exposure to the cold you're getting and how much sort of sympathetic activity you're getting to drive it one way or the other. But I think this is sort of a simplified view of it, but I think there's probably a number of other things playing to it. But I think that's the main thing.
I think a simplified view is the right view for me at this stage, because I'm an engineer. I work on machines. I work outside the body, and you work inside the body. When I'm going really well, I'm trying to understand how the environments that I will create with my machines make changes inside the body. And you brought up the sympathetic division of the autonomic nervous system. This should lead us to be curious about how brown fat is attached to the nervous system. It is highly innervated compared to white fat, and it responds to the nervous system in ways that are surprising. Will you describe a little bit of that connection?
Yeah, so I mean, we know that that's the defining feature of brown adipose tissue in particular is that it's very innervated, so it has a lot of nerves that go through it, and most of those nerves are from our sympathetic nervous system. So the way that typically works is that in the context of cold exposures, typically we have sensors in our skin that will respond to temperature, hot and cold. But when it comes to cold exposure in particular, you'll get a sort of a strong stimulus from the skin cooling, which will send a signal up to your hypothalamus saying, you're experiencing this cold stimulus. And the hypothalamus will sort of integrate not only the information coming from the skin, but also what's happening internally. So there are also sensors within our gut, our intestines, along our spinal cord, which tell us whether it's cold or hot. Particularly, these are particularly those that are more sensitive to the heat. So they often tell us, are you hot enough? Or are you starting to lose heat? And so the hypothalamus sort of integrates all of that. And if it reaches a certain threshold, then it'll say, well, it seems like your internal temperature is maybe not being as stable as it should. And so we should probably start activating mechanisms that are going to help generate heat. And so that's where the quickest response is to stimulate the sympathetic nervous system, because it can quickly lead to vasoconstriction. So right away, it'll reduce how much heat you lose to the environment. And at the same time, it creates a very quick method of producing heat. It's a very, very quick response, because basically all you do ends up happening is that you have these nerve terminals. They release a lot of norepinephrine, and then the norepinephrine will bind to these receptors, which will activate the tissue. It'll lead to vasoconstriction, or it'll lead to brown fat, in this case, starting to generate heat. And so this process is very, very quick compared to, for example, shivering, which is a much longer process. And so basically the body's trying to find a quick way to limit how much heat we lose and to try to generate as much heat as possible. Now, once the norepinephrine binds to these receptors, it's not automatic. It's not just they bind to the receptors and then we produce heat. Ultimately, what it's doing is it's creating, it's breaking down triglyceride molecules within our tissue, which creates fatty acids, and then those fatty acids will then activate a protein in the mitochondria that says, okay, well, we need to start generating some heat. So this is the process that starts generating heat in the mitochondria of brown adipose tissue. It's a very unique feature because this protein is only present in brown adipose tissue. It's not present in other tissues. And that's sort of the other distinguishing feature of brown fat, is that not only that's very innervated, it's very vascular, it has a lot of blood vessels that go through it, but it has a special protein inside called uncoupling protein 2 that is responsible for its capacity to generate heat. And that's what really gives it this key feature.
Now, you emphasized the breakdown of triglycerides into fatty acids that then are the fuel for metabolic non-shivering thermogenesis inside the brown fat. Triglycerides are interesting because we know that high triglyceride levels in the bloodstream are associated with heart disease. And so one of the mechanisms by which we consume these triglycerides might be non-shivering thermogenesis. But why do you emphasize the fatty acid metabolism instead of glucose?
Yeah, well, I mean, in part it's because the tissue will often rely on what it has available. And the tissue itself, what it has highest level of is triglycerides. It will take up glucose when it needs to, but it's often when it takes up glucose from circulation, it's largely to regenerate triglycerides, which it needs to produce energy, or it uses the glucose to generate the backbone of a triglyceride molecule. So it's often all with the purpose of, and I hate saying purpose because it's not purposefully doing this, but anyway, but it's taking up glucose to create triglycerides so that it can use this triglyceride to fuel itself. And I think that's again, a lot of the misconception that we have as well. This brown fat takes up a lot of glucose, and so therefore it's oxidizing it right away. Well, it's not really oxidizing glucose. It's taking it to create triglycerides, which it then uses as fuel. So it's really important. If you block this triglyceride from doing its job, from breaking down or from forming, the tissue stops responding altogether. Amazing. So we know that these triglycerides within the tissue are so important, and they're vital to its function, because if you cut off its ability to release fatty acids, so prevent it from breaking down the triglycerides, or you prevent it from forming triglycerides, you will not be able to activate the brown adipose tissue.
This might help explain something. There are two things that happen in the bloodstream. I've got continuous glucose monitoring data and continuous ketone monitoring data, because there are now new devices. And the two things that happen is, as soon as you get into the ice bath, typically there's a glucose spike, and then it comes way back down. Mm-hmm. In type 2 diabetics that have chronically high blood glucose levels, there's no spike. It just starts coming down. But the other thing that happens is continuous ketone monitoring data shows that when you get into the ice bath, you get an immediate or nearly immediate boost in ketone levels. And that's an indication that fat metabolism is happening. What you're saying is that clearing the glucose from the bloodstream is happening by brown fat, but that the brown fat are converting that glucose into triglycerides in order to fuel this uncoupled reaction, this non-shivering thermogenesis inside the mitochondria?
Yeah, so I think there's a couple of things to keep in mind. One is the decrease in glucose that we see in the cold is actually primarily driven by glucose being taken up by skeletal muscle, not by the brown fat, in part because there's not enough brown fat. So most of the decrease that we see in glucose levels when someone is exposed to the cold is actually our skeletal muscles taking up glucose to fuel the shivering part. It's not actually brown fat itself. Brown fat accounts for about less than 1% of the whole amount of glucose that our body takes up, whereas the skeletal muscle could be up to 60% or higher. So most of that decrease is from that. The changes you see in ketones, the ketones are often a reflection of incomplete oxidation of fatty acids. So when you have a high supply of fatty acids, particularly in the liver, then you have this high amount of ketones that are produced. And so what often happens in the cold is that you have this high release of fatty acids in circulation. They make their way to the liver. The liver will probably say, well, this is too much. And so it may produce ketones. Those ketones will eventually be oxidized as well, eventually. But that's a lot of this is sort of this high flux of energy. There's so much energy going into circulation and going to certain organs. The adipose tissue is playing a certain part in taking up some of that energy out of the circulation, and it will use that energy to fuel itself. But like I said, it's on a whole body scale, it's a small player on the clearance of either glucose or fatty acids or ketones or triglycerides, regardless of what it is, in part because there's not a lot of it. We're talking about anywhere from 50 to 150 grams of tissue spread across the body. And this is where we have a bit of, where our group tends to disagree a little bit with the field is what role is brown fat playing on whole body metabolism, but we can maybe get into that later.
Well, now might be a good time then to ask you about the relationship between brown fat and insulin sensitivity, because we know those individuals who have more brown fat are typically more insulin sensitive, or another way to put it would be less insulin resistance. How does recruiting brown fat improve or change your insulin sensitivity?
Right. So I will answer that with a somewhat circuitous way. So what we often see in the literature is indeed that when you look at sort of these retrospective studies, so studies where you have patients who have gone into the hospital often for cancer diagnostics, and they undergo these PET scans. And usually for these PET scans for cancer diagnostics, they'll usually receive a glucose tracer because it helps to show up where these tumors are. But at the same time, it also allows to see, spontaneously, you'll see in some individuals, you'll see some brown fat activity. You might have a cohort, let's say, of 5,000 participants, and maybe about 500 or 200 or 300 of those will have this spontaneous activity. And so what ends up happening is that we'll do, different groups will look at, well, what's the relationship between those who seem to have this spontaneous activity of brown fat and those who don't? And that's where you see a lot of relationships where we see, well, those who seem to have this spontaneous activity of brown fat are more insulin sensitive, they tend to be leaner, they seem to have better metabolic profiles, so better triglycerides. So all of those things all pop up. And they all seem to correlate with a better, more of a presence of brown fat seems to have a better effect on our metabolism. They have a better cardiometabolic profile, so blood pressure and those sort of things. It would be easy to assume that because we see these associations, these correlations, that brown fat is causing these effects. The problem is when you do these experiments in individuals, where you actively stimulate them with the cold, you realize that it's not possible. It's not like, well, maybe there's some debate. It's not possible. There's no way that it can work that way. So our way of viewing it is, what we still have to realize, we still see this association. Something must be happening that is consistently presenting with this strong association between the presence of having brown fat is giving people a better metabolic profile. But if it's not brown fat that's causing this, then what could be causing this? And what we've hypothesized is that the brown fat is your canary in the coal mine of how our adipose tissue works. If your adipose tissue is healthy and it's clearing triglycerides, so if it's clearing dietary fatty acids from circulation, so after you eat, rather than having it stored in lean tissues like the muscle and the liver, where it can cause problems on insulin signaling. Well, if your adipose tissue is healthy, it will store it where it should be stored. Whereas if your adipose tissue is unhealthy, then it will not store triglycerides as well. And so therefore you'll find it in other organs like the liver and like the skeletal muscle, which then leads to insulin resistance. So our hypothesis is that the brown fat, because it's so metabolically active, is very, very sensitive to very small changes in metabolism. So for example, we undertook this study where we had participants go on a high fructose diet for 2 weeks. These were healthy individuals. So, relatively active, relatively healthy profiles. And we gave them a diet that was rich in fructose for 2 weeks. So it's not long enough that you're going to see weight changes, but it's long enough that you start seeing changes in triglyceride profiles. And we thought it would be long enough to also see changes in brown fat. And sure enough, we did. So we didn't start seeing major changes in white adipose tissue. There were hints that the white adipose tissue was starting to be dysfunctional, but because it's spread out across such a large volume and it's such a large amount of adipose tissue, you really need big changes to see small changes in white adipose tissue. Whereas the brown fat is a small organ, And so if it's very, very sensitive to metabolic changes. So what we found is that that organ was very, very responsive. We were starting to see dysfunction in the brown adipose tissue that we were not quite seeing in the white adipose tissue yet, in part because it was like our early indicator that things are not going well metabolically. And so this is what our explanation, what we think is happening, is the reason you see these associations between having brown fat and having this better metabolic profile is that it's not that the brown fat is causing this, is that the brown fat is an indicator of the health of adipose tissue in our body. So the healthier your adipose tissue, the healthier your brown fat will be, the more likely it will be to take up glucose, and therefore then you'll also have this better profile. Whereas on the flip side, if your brown fat is very rich in triglycerides, is over full with energy, it won't take up as much glucose. It may be resistant to insulin. And it's very likely that it's also reflecting the fact that not only is the brown fat full of energy, but the white fat is probably overflowing with energy as well, in which case then it's having to send energy elsewhere, where it's causing insulin resistance in the skeletal muscle and in the liver. That's where we sit on that. But like I said, this is not the common view, I would say, but it should, in my opinion, it should be.
Then in your view, brown fat and insulin sensitivity are both downstream of a general adipose function. If the adipose tissue in general becomes dysfunctional, the brown fat either disappears or becomes dysfunctional, and insulin resistance increases. Rather than brown fat being the mechanism that controls insulin resistance, these are two different indications of overall adipose tissue health.
That's right. Yeah. So the brown fat is really like I said, the canary in the coal mine. It's the first thing that's going to go. It's the first thing that is going to have problems before you even start to see major changes in white adipose tissue. Again, you'll see like a flickering. You'll see, something doesn't look quite right in that white adipose tissue, but in the brown, it'll be clear. There's something going on. And so that's where, it's really, it's great for that, because it really gives us an early indicator that there's something happening in the white adipose tissue that if we don't interact or intervene right away, you'll start to see major effects on the white adipose tissue, which will then have downstream effects on insulin sensitivity in the skeletal muscle and the liver, which are really the drivers of, when we talk about sort of the impact of why insulin resistance is a problem for diabetes, and why exercise is so good. Well, it's because it's happening in the muscle. The muscle is so important in clearing glucose that by exercising, you're helping the body clear glucose. And you're making it more sensitive to insulin. And at the same time, you're also making the adipose tissue more sensitive to insulin, because now you're taking the burden and the load off of it by oxidizing substrates.
I should interject that we care about insulin sensitivity, or the converse, insulin resistance, because it is associated with every leading cause of death from chronic illness in the United States. The insulin resistance, which we could call an epidemic, that is at some level evidenced in some 90% of the American population, and to a large extent Canadians as well, is at the origin of chronic illness. And that is one of the most important factors in the reduction of life expectancy that is experienced or been experienced in the United States since it peaked in about 2014. And so the explosion of research in brown fat since about 2012, when you and other groups began publishing on brown fat, has looked at brown fat as if it would be a therapeutic target. Could we target brown fat either pharmacologically or through diet or through cold exposure, although very few people seem interested in cold as you are? Could we target brown fat as a therapy for insulin or metabolic dysfunction that would help us treat all of these chronic illnesses that are shortening lifespan? I think you have some views on that because you recently published a paper.
Yeah, I mean, I think, again, that I think has been the objective since the beginning, right? It was this idea that if you can we grow brown fat? Can we target brown fat either pharmacologically or through lifestyle interventions, whether it's cold exposure or other means? Can we make this tissue grow? Because if we can make it grow, it will just help to burn off extra calories. So it'll prevent this oversupply of energy from accumulating in organs where it's not supposed to be. And this is a great idea theoretically, and it works beautifully in the rodent model. It works really, really, really nicely in rodents. It's probably the best way to get a rodent to lose weight is you grow its brown fat. You think of any way you want to do it. There's lots of ways to do it, and they will
You
lose
can
weight.
even transplant brown fat into a rodent and see metabolic improvements. I've read some of
Absolutely.
those studies.
Yeah,
Yep.
absolutely. So it's very, very fascinating and impressive in rodents. The challenge we've had is the ability to translate that information and those interventions to humans. They don't translate, and I think part of the reason they haven't translated very well is one, we thought we knew the targets. The primary targets, like I mentioned, is normally we think about when we activate brown fat. I'd mentioned norepinephrine will bind to these receptors on the surface of the adipocytes, which are responsible for activating the tissue. So in the literature would often say, well, the brown fat relies on this one specific receptor, the beta-3 receptor, to activate brown fat. The problem is humans don't have this receptor in brown fat. So we've been targeting this protein, this receptor that isn't even present in the brown fat of humans. And so this was one of the discoveries.
I don't know
that we
why
made.
I'm laughing, Dennis. That's like a scientific tragedy.
Oh, it is. If you knew the amount of money that went into pharmacological research to try to target this receptor that actually isn't even present. And so a lot of people lost a lot of money trying to target a receptor that actually isn't even present. And I think this was thanks to work that we did with our collaborator in Copenhagen, Dr. Camilla Schiel and Soren Nielsen, who really helped us discover that, in fact, it's a beta-2 receptor, its cousin, that is far more present in brown adipose tissue. It's the same receptor that's also present in white adipose tissue. And so this, so number one is you need to find the right target. So we didn't have the right target, so that was part of the reason we were having issues. Then you have to think about, well, can we make this organ grow? How can we make it grow? The problem is that when you look at it even from, the strongest stressor you could do, better than any kind of pharmacological agent you can give, is cold exposure. And you expose people to cold every day, 2 hours a day for a month. It's a lot. It's a big investment. It's a big time commitment. And they're only increasing the size of the tissue by 40%, which seems like a lot. But when you're going from, you're going from a tissue that's about 50 grams, you might go up 50% of that. So maybe you're out now up to 60 or 70 grams. It's still not a lot. And you've just committed 4 weeks. So we're having a hard time growing this tissue. And I think that's the other part. The big issue we have, if we really want this tissue to be a target for weight loss and a target for improving metabolic health, we have to find ways of making it grow in an efficient way. Thankfully, there are some groups in Boston right now that are working on that. There's a few different groups in Boston, I think in Texas and in Copenhagen, who are working on ways that we can try to grow this tissue in an efficient way. And I think that's where the focus should be, is how do we find ways to increase the size of this organ? The one caveat is that there is evidence, there are clinical indications of groups who have a lot of brown fat. So there are individuals who have a condition called pheochromocytoma, where essentially what it is that you have these tumors that release high amounts of norepinephrine, and what they end up doing is they end up having these large amounts of brown adipose tissue. Really, really impressive. It's huge amounts. It's the highest sort of documented amounts of brown fat you see are in individuals who have this condition, the pheochromocytoma. But strangely, they don't have good metabolic profiles. They are very hot all the time. And it has to be treated. And so normally what they do is we remove the tumors because, and when by removing the tumors, it actually improves their metabolism. They're not as hot. And so you have this weird paradox. On the one hand, we want to target brown fat because we think it'll help metabolism. But on the other hand, you have this population where we know they already have a lot of brown fat. And in fact, they're in not a great metabolic state to begin with, despite the presence of a lot of brown fat. Maybe it's one of those cases where it's too much of a good thing in that case. Maybe it's just too much.
There are many such cases. Yep.
Right? So maybe it's that the reason why they don't have the profile of what we would expect from someone who has brown fat is because they have too much of it. Yep. And so maybe there's a happy medium. Maybe there's a medium somewhere where we have to have the right amount where it provides us with the protection that we want, and without having the deleterious effects that you see by having too much of it. Where that is yet, we don't know, but
let's talk about some of those studies in cold exposure intended to recruit brown fat. One of them is out of Germany, Hansen et al. He has got this group where he took these, obese, middle-aged German men. I'm going to call them middle-aged because I'm 59 years old, and they said, look, don't exercise, don't change your diet. Just sit around for a few hours in a t-shirt and shorts. You can watch your football game, whatever you want to do. And they saw over 2 weeks, I think it might have been 10 days. They saw big improvements in glucose sensitivity. They were able to observe metabolic changes. And I think that's wonderful. But I'm like, sit around for a few hours, at 55 degrees Fahrenheit or something. They didn't even report being uncomfortable. Very few of them said that they shivered. I'm like, get yourself into a dang ice bath, with ice float, 0 degrees Celsius. You only have to spend 3 or 4 minutes. You'll get some brown fat. I'm looking at those experiments coming out of Germany and Europe saying, well, that's wimpy cold. And part of this is because I own an ice bath company, and not every 60-year-old type 2 diabetic obese German man is going to sign up for a plunge in one of my ice baths. But could more extreme cold create a stronger sympathetic nervous response and a more rapid recruitment of brown fat into the human body?
Yeah, so I'll answer that sort of in two parts. I think the short answer is we don't know. There's been a strong emergence of cold plunges over the last 4 years, and a lot of the benefits that we hear a lot in the media about, here are the benefits of cold exposure, are actually not based on cold plunge studies. There are actually not a lot of cold plunge studies. So one of the big things that we don't know is, we don't know how intense do you have to do it, how long do you have to do it, how frequently do you have to do it, at what time intervals or what duration. So there's a number of things, the FIT principle that we talk about for exercise, we don't know that for cold exposure. Right. Do I believe that you could probably do a cold plunge, you could have the same effects if we did a cold plunge every day versus having, for a short period of time versus having a longer period of time in these cold rooms? Probably. But we don't know for sure. So, scientifically, that comparison hasn't been done. It's plausible and it's very likely, but it's not been done. I think we have to be careful that when the literature that's really out there, the literature that's published, is often not using cold baths, for one, in part because we're trying to get at mechanisms that are difficult to get to when you have someone in a cold bath. So it's often done in a cold room. We use neither a cold bath nor a cold room. We use a cooling suit. Which is different. Okay. And there's a reason behind that. It's because we treat it like a treadmill. So it gives us very precise control that you don't get with a cold room or a cold bath. So yeah, so the short answer is, could you do, if you did a short cold bath versus a longer duration cold room, could you get the same effects? Probably, but the data has not been done yet, or the research hasn't been done yet. The other part I would add to this is, what's also interesting from this group. So this is a wonderful group based out of the Netherlands, out of Maastricht University in the Netherlands. And so they've done a few different studies where they've done these 10-day cold acclimations in individuals either who were overweight or obese, or individuals who had type 2 diabetes. And they've done a few different interventions. Interestingly, the first intervention that they did for 10 days, it was a bit colder, and they found there were improvements in insulin sensitivity as early as 10 days, which is actually quite remarkable, because even with exercise, you don't see the changes that you see with this cold intervention.
Agreed. Yep.
And so, but what was interesting is that the amount of brown fat in those individuals actually didn't change much, and the uptake of glucose also didn't change much. But what did change was that there was an increase in GLUT4 translocation. GLUT4 is a protein that is responsible for taking glucose in skeletal muscle. So when we talk about the benefits of exercise for individuals who have type 2 diabetes, and we talk about improvements in insulin sensitivity, it's driven by the presence and the increase in this GLUT4 transporter, this glucose transporter. So what they found is in 10 days, they saw an increase in both the total amount of this transporter and the presence of this transporter at the membrane of the skeletal muscle. Now, they followed some of this study up with a few other cohorts where they did it less cold. The cold exposure was less cold because they found we don't want the shivering, because we feel the shivering is uncomfortable. We don't want as much of it. And they didn't see those improvements. So what it goes to show is that if you want to see improvements in glucose regulation by using cold exposure, you need a certain level of muscle tension or shivering. Because in the absence of that muscle shivering or muscle tension, you don't get those metabolic improvements. So again, it's further evidence that do cold exposure because it'll help your health, it'll help your metabolism, but let's not conflate the improvements we see with metabolism with benefits that are coming from brown fat. Brown fat is certainly increasing in size and activity and doing lots of things, but when we look at the whole body systemic effects, it still remains too small to have a major effect. A lot of the major benefits, metabolic benefits that we see with cold exposure is coming really primarily by having shivering skeletal muscles. If they don't shiver, it's like doing sort of low grade exercise.
Fantastic, Dennis. You are helping us understand for anyone who's listened this far, the metabolic consequences of cold exposure. But in the time that we have left, I want you to help me understand brown fat in all of its other functions. By now, the role of brown fat in metabolism should be uncontroversial, no matter what you hear on Instagram. It is well established. What's even more interesting is that brown fat is a secretory organ and a signaling mechanism for other metabolic aspects of the body. This is the real, I think, leading edge of brown fat research, and I'm hoping that you can help bring me up to speed.
Yeah, so I will say, so both I think amongst my colleagues in the field of brown fat and sometimes outside of the world of research, we are often considered as those sort of the black sheep and the haters of brown fat. And this is where I would like to set the record straight, is that what we are saying is that where we think brown fat is very, very impressive is, like I said, not only is it the canary in the coal mine, but where we do think it's having a protective effect is because of its location. So I'd mentioned before that brown fat is located often in different areas. And those areas, so I'll mention, we talk about the supraclavicular area. Now this area, it tends to envelop the carotid arteries. Then you have some adipocytes, so individual adipocytes, brown fat cells that are often near the heart, so sort of just outside of the heart in the epicardial region. Then you've got some around the kidneys. And so when you and then sometimes in some individuals you have it along the spinal cord. You piece all of those things together and you can hypothesize that maybe what it's doing, its primary function remains to produce heat. So definitely in a condition of hypothermia, having those adipocytes in those regions is going to protect those organs to remain warm. It's going to ensure that the brain remains warm and functions properly by ensuring there's warm blood going to the brain. It will ensure there's proper neural conductivity along the spinal cord. It will ensure that the heart remains at a temperature that it should be working at. It will also ensure that the kidneys are functioning in the way that they're supposed to and staying warm. So you can see it's very protective in by generating heat. But the consequence of also generating heat is that it also requires taking up a lot of energy. So we also find that having those adipocytes, those brown fat cells, near those organs is also protective metabolically. So it may protect the heart from having too much energy going towards it. So it seems to be protective in burning off extra energy. It seems to also protect the heart from developing inflammation. And then we see the same thing with the kidneys. We see that in the perirenal depot of brown fat, we see that it seems to be very protective from developing inflammation, from developing, from having too much energy going to those organs. We also see in the visceral fat depot, there's a certain area where there seems to be more brown fat as well. Again, it seems to be very protective in those areas. Same here, we expect that the brown fat, by not only is it going to be generating heat to go up to send warm blood to the brain, but it's also probably potentially has the potential of protecting the brain from having too much energy as well. So we think, again, not only is the brown fat the canary in the coal mine, but we think it has a very regional effect. We don't think it can have a whole body effect. We think what it does, it has very local effects and protects vital organs. And that's why you tend to see this association again between the presence of brown fat or not and this metabolic profile. By having brown fat and having this better profile is probably because you also have several depots of brown fat across the body, which is protecting these organs from developing complications. And I think that's where it's very important. And to your point as well, not only is it having a local effect in terms of generating heat and protecting those organs from too much energy, but it also releases compounds, hormones, proteins into circulation, which may have an effect locally, either to the organ that it's attached to itself, or to more distant organs, whether it's skeletal muscle or the liver. And so, that's another situation where you don't need a large organ. The thyroid is a perfect example. You don't need a large organ to have a big impact on metabolism. So you can still potentially have the tissue itself may still have an effect indirectly by releasing these hormones and inducing these whole body effects through the release of these hormones. The evidence for that is a little bit less strong. Yeah, in the same way with the thyroid, but the evidence for that is less strong, but it's still evolving.
There is an interaction between the thyroid and brown fat. One example, probably the most obvious, is that active brown fat will convert inactive thyroid hormone into more active thyroid hormone. But that's not the only mechanism. How do brown fat and the thyroid communicate to regulate metabolism?
Yeah, I mean, that's a good question. I mean, this is pulling me a little bit more outside of our area, but I think that, again, a lot of it I think is very indirect. We think that either there's very likely some communication, or more likely that, again, there's some commonalities between the two. Again, like you mentioned, in brown adipose tissue, there's an ability to convert an active form of thyroid hormone, but this is thyroid hormone that's produced by brown adipose tissue, not necessarily coming from the outside. Although it may also do the same with thyroid hormones that are coming from the outside, from the thyroid. But a lot of this is thyroid hormone.
Let me clarify, or let me ask to confirm my understanding. You're saying that brown fat is capable of producing thyroid hormone, not just converting it, but making thyroid hormone inside its own cell.
Yeah, it's not huge amounts. It's not like the thyroid hormone, not like the thyroid itself. It's not going to generate huge amounts of thyroid and contribute significantly to the circulation. But my point being that more that it can produce it and then convert it within itself, and can also take up the inactive forms of thyroid hormones to activate them. But often it's used very locally. But again, like I said, it's not going to be dumping huge amounts of thyroid hormone in circulation. It's not a thyroid. But there seems to be a strong link between the two for sure.
Mm-hmm. There's another organ that might pull you out of your core area of expertise, and that is the brain. There's no brown fat in or around the brain. You've pointed out that it has to be in the blood vessels that supply the brain, so that if the brown fat is thermally active, it will warm that blood to help keep the brain warm. And yet, higher levels of brown fat are associated with higher levels of neuroprotective factors, whether that's brain-derived neuroprotective factor or FGF21. There's some relationship between the brown fat and the brain, and in particular, brain health, the recovery from brain trauma, that we have yet to decode.
Yeah, I mean, I think that's still, again, there's a lot of work starting to happen now in Finland, in Turku, with the group of Kirsi Virtanen, who they are starting to look a lot more closely at what are the relationship between brown fat activity and brain activity. So I think we'll start to see a lot more of that work come out in the next few years. But again, my thought is essentially that it's like the brown fat, because the brown fat in the supraclavicular area really goes around, it wraps around the blood vessels. Probably what it's doing is it's creating a nice gateway. It's a clear gateway into the brain to ensure that we've got proper blood flow that's not restricted, that we've got clean blood flow where you don't have high amounts of triglycerides as much, because again, maybe it's more protective. Again, this is all speculative; we don't know for sure, but this is my hypothesis on this, is that it's kind of that barrier that it's almost like a dam, right? It's going to protect, it's going to preserve, or almost like a filter that's going to ensure that there's a clear sort of pipeline going to the brain. And I think that's where it's having probably quite a significant effect. But maybe there are other factors as well, that maybe the brown fat is releasing things also that are making their way to the brain, or vice versa, that allows them to have some communication. I think we also can't overlook the communication. We think of the communication as being just the sympathetic side of the nervous system, but we also have to think that there are also sensory nerves, so nerves that go through the that provides some feedback that we can't overlook. So we had a great presentation last week here in Sherbrooke from a group from Christy Townsend from the Ohio State University, where she talked a lot about the impact of sensory nerves in adipose tissue. And I think that's the part that often gets overlooked that I think we have to look at as well. So how does that, because what it does is it ensures that there's, again, proper function and communication with the organ of interest, whether it's brown adipose tissue or white adipose tissue. If you have a dysfunction in sensory nerves, it can lead downstream to having problems in the function of the tissue. And I think that's where that work really is quite important. So there's really phenomenal work being done from her group and others in that area.
There's a lot going on in metabolism and mental health right now. So there's Chris Palmer out of Harvard. He wrote his book called Brain Energy. But there are other people, perhaps less popular, but also working on the relationship between metabolism and mental health and learning how to treat mental disorders metabolically. Is there a relationship between brown fat and mental health?
So I would say that at the moment, the link with brown fat specifically is not clear. I think what we're seeing right now is that there's again, really great work starting to happen now in the UK with this researcher named Professor Heather Massey. And so she has started doing some work where she's been looking at the effects of cold plunges or what they call winter swimming in Europe, which is essentially cold. They're often swimming in sort of, harbors, or you see it especially in sort of Copenhagen and Helsinki. You see these sort of where there's basically swimming in harbors throughout the year. But what she's seeing is that there are improvements in mental health for those who follow winter swimming. And so I think for anyone who's done cold plunges, this would not be a surprise to them. Everyone talks about how good it feels, how good they feel when they do their cold plunges. Again, I don't do a ton of cold plunges or cold showers. I do them, somewhat, but I don't do it every day. But anyone who does it will say that that's the primary reason they do it, is they feel good mentally, right? And I think what we're seeing is now some of the work from Heather Massey is starting to confirm some of those things. So in one of the studies that she's been running, she had a group of individuals with clinical depression, and she's been having them follow this winter swimming program, and they're seeing, remarkable improvements in their mental health, in their depression symptoms, their affect, their overall, well-being. Now, again, it's hard to dissociate that the cold from the fact that it's a group activity. So part of it is probably explained from the fact that it's a group activity, but I think a large part of it is probably more related to the winter swimming, the cold water itself. And I think that part is really interesting. So I think it confirms to a lot of people who've been doing this for a long time the impact of doing these cold swims. Now, whether brown fat is involved in that, I don't think it would be necessarily directly responsible for it, but I think it's active, so it'll be associated. But I think regardless, I think it's clear that when you expose yourself to the cold regularly, you see these improvements in mental health. Again, we have to come back to the idea, though, but how frequently? Is it something that has to be done every day? Is it better for it to be done every 2 days? How long? How cold? Those are all questions I think we still have to ask.
So I want to ask you then about your own practice. You say every once in a while you'll do a cold shower. Now that you're into this for 15, 20 years of research, and you've piled up such an impressive scholarly record, is there something that holds you back from doing your own ice baths, or I don't know, jumping in the St. Lawrence River every once in a while?
Yeah, I mean, I love the cold. We do a lot of winter activities in the winter. We are avid cross country skiers. I love the cold. In the winter when I'm shoveling, I will often shovel in t-shirt and nothing else, in part because we generate so much heat. So I love the cold. I don't do it every day, in part not for any particular reason. There are some concerns that we some risks that we think we need to explore a little bit more carefully. One of which has to do, I talked about the sensory nerves. I have some concerns with what is the risk of doing cold water plunges every day. Are there risks to our sensory nerves? We don't know. it could be, maybe we don't, maybe not. That, and then that's my only sort of concern is, should it be done every day? I don't know. But I think that's why we have to do this research, right? I think it's one of those things that we have to figure out. How much, is it like pheochromocytoma? Can there be too much of a good thing? Because we know that people, will like exercise. Exercise is the same thing. Yes, you want people to be physically active and exercise every single day. But, we know that there are people who can overtrain and overdo it. And so
there is too much of a good thing. There's too much exercise, there's too much cold exposure, there's too much sunshine, there's even too much sleep. That everything. But
on the flip side, I want to say just that I think I've seen benefits of cold exposure. It's part of the reason we've gone down this route, because we were the first ones to really identify very clear metabolic benefits of cold exposure. And we'd been sort of talking about it for a long time before even a lot of the brown fat stuff was happening, saying there's something interesting here. Exercise is not for everyone. Not everyone can do it or wants to do it. But are there other ways that we can improve people's health? And cold exposure seems to be one of those ways that we see some benefits. And I think we see, even on the academic side, there's a lot of people who start kind of poo-poo it and say, well, it's so mainstream. This is such a Joe Rogan thing. This is such a, a bros thing. And but there are very clear benefits that you can't overlook. And I think we're at the point now where we have to convince clinicians to say, you can't just prescribe physical activity and exercise to everyone, because not everyone wants to do it. This is a viable option for certain populations. If you're not at risk of cardiac complications, if you're not at risk of arrhythmias, it could be of benefit to those individuals. And it might be the boost that they need to start being more physically active and getting into exercise. But yeah.
What your lifestyle points out is, in Montreal, it doesn't have to be an ice bath. I mean, I live in the hottest city in North America. I need the ice bath because I'm never going to be shoveling snow. But for you, you can have seasonal cold exposure. You put on a t-shirt, maybe some jeans, you go out and you shovel your driveway, and you're going to get your cold. The fact that you're exercising in the cold compounds, I'm speculating, but compounds the metabolic benefits. You don't have to be in an ice bath or in a cold shower. However, for some reason, there are 5 million people living in this valley in Arizona, and they do not have access to the kind of seasonal cold exposure that a body like mine is expecting. This is a perfect opportunity for a machine like a Morozko to fill in that environmental gap. Ironically, it might be more important for cold in the winter than in the summer. The weird thing about Phoenix is it's so hot here in the summer, people don't go out in the sunshine. There are vitamin D deficient people in Phoenix, Arizona, because they're not getting enough sun. So there are some industrialized infrastructure elements that disconnect us from the environment that would keep us healthy. Mm-hmm. One of the things that we can do is use technologies to restore that connection. I sometimes say Morozko is the next best thing to nature. And of course, I love getting in my ice bath. When it's 45 degrees out and I'm hot and sweaty and I've just been walking all over campus, it's a huge relief. It might be even more important for me to get in the ice bath in January and December, when there's less sunshine, when I'm sort of less inclined to do it, when I'm less comfortable doing it. But I might be getting more of those kind of seasonal metabolic and mental benefits. In your case, I remember those days of shoveling. In your case, it's ready for you anytime you want it in the environment. We sell quite a bit into Toronto. I don't think we've sold anything into the province of Quebec. And why should people spend, $12,000 if they could get the same benefit shoveling their driveway? It makes sense.
Yeah. My message to a lot of people is that I think we have to get used to just feeling a little bit uncomfortable. I think we're in a society now that is not used to that. And I think there's a benefit to feeling uncomfortable. I think you have to feel uncomfortable, whether it's thermally, especially. I think we're too used to having these very carefully controlled environments. And I think that's part of the reason I think we're experiencing some of the metabolic diseases that we're seeing, is that we're too used to things being too regulated. I think we have to be uncomfortable for periods of time. And I see the benefits of cold plunges in forcing you to feel uncomfortable. It will build resilience for sure. And we see that the improvements metabolically. And I think we can do it intelligently. I think we can find ways that we're getting the benefits without overdoing it. But I think we got to push people and push ourselves to feel uncomfortable, be comfortable in feeling uncomfortable.
Right now, this stigma of like bro science or that's too Joe Rogan is an obstacle to some people accessing these benefits. They'll call it a fad or they'll dismiss it as a social media phenomenon, and they won't realize that there are hundreds of scientific citations underlying the kinds of things that we're talking about. I hope we break down some of those stigma and we correct some of the misconceptions.
Yeah, well, thank you so much for the opportunity to share that information with you and to have this discussion with you. I think it's interesting to have this discussion with you.
This was brilliant for me.
Great, thanks so much.